So, good evening, everyone. Welcome to this NPTEL session for the course Robotics Basic Selected Advanced Concepts. And this is essentially a problem solving session. But what I'll be doing is, as I've done in the previous weeks, I will discuss the lecture notes and just point some of the relevant information in those lecture notes that will help you solve the assignment and also give some insights related to the topics that are there in the lecture notes. So, to begin with, I will just list out what was on. Like, this week was all about, you know, modeling, analysis, and control of wheeled mobile robots. Okay, so like the first chapter starts with pretty basic scenario that you have a simple wheeled robot and it starts with a single wheel case on a flat terrain. Okay, so if you just go through it, there are some basic information about the current state of the research given in some of these slides, and then there is the discussion for single wheel kinematics. Okay, so in single wheel kinematics, okay, what the initial case that has been considered is that if there is a wheel that is on a surface, okay, so the wheel can own if it is rotating. Okay, so it is rolling without slipping. Okay, and what do we, well, this is the first case that it is rolling without slipping, and the second constraint is, so this is the constraint in this direction for now. Okay, so it has been analyzed in the subsequent slides and subsequent discussion that what happens if this thing is violated, if the slip actually occurs in this direction, okay, in the direction of motion of the wheel, but there is another direction in which the motion must not happen. Okay, that is the direction perpendicular to the wheel. Okay, perpendicular to the face of the wheel. So this is the second constraint, this non-holomorphic constraint that is being talked about here. Okay, so now this is a constraint on the velocity, right, and not on the position, because the wheel can be anywhere on this 2D plane. Okay, but wherever it is, okay, it cannot, the velocity of the wheel in this direction, okay, has to be zero. That is what it means for this point to just stay here. Okay, so now this constraint will be a function of all these three quantities, right? The velocity of the center of mass of the wheel and the rate at which the wheel turns. Okay, so this phi is not the angle of the wheel. Okay, it's not the angle traveled by any point on the wheel, right? Because of the rolling of the wheel, it is because of this rotation, overall rotation of the wheel. Okay, so this is phi, and this will actually constrain, okay, what should be the velocity. So basically, the component. So if you try to look at it from a 2D perspective, okay, so let us say that this is the wheel, okay, and there is an inertial frame. So this always helps, okay, to just draw the frames and then try to reason about what the constraints are on the system. Okay, and we say that this system, okay, it has been rotated by an angle phi. Okay, so this is the angle phi that is being talked about here, and this is your body coordinates, okay, or the body basis vectors small e1 and small e2. Okay, and so what is the constraint? Okay, velocity along e2, right, should be 0. Okay, so now if I write the velocity of the coin as vc in the vector form, so the velocity along e2. Okay, so this is the constraint in English. Okay, what is it in math? Okay, so this is the constraint. Since we've already written hat, we'll not use under bar. Okay, so this should be equal to 0. Okay, this is the constraint that we have here. Okay, and what is vc? Okay, so vc is just the velocity of the center of mass of the wheel, or like not just the center of mass, it is the velocity of the point of contact of the wheel. Okay, but when we are talking about e2, for that point of contact, we are not going to take into account the rolling velocity of the wheel. Okay, because again, at the point of contact, we are assuming that this is also 0. Okay, so the overall velocity is only governed by the velocity of the center of mass. Okay, so you know what is essentially the constraint? So your VC is x dot, y dot, and 0. And what is E2? Okay, so dot product with. So E2 written in the base frame will be your, okay, so how do you write E2? Okay, so EI is just RZ phi capital EI. Okay, so this RZ will lead to what? Minus sine phi, cos phi, and 0 for E2, right? Because this R is C phi minus S phi, S phi, C phi, 0, 0, 1, 0, 0. Okay, so this is basically your E2, right? Small e2. When you make it 0, it comes out as minus x dot S phi plus y dot C phi equal to 0. Okay, and again, you can see that this is the type of constraint that has been talked about here. Okay, and this is a non-holonomic constraint, and about non-holonomic constraints, I has talked in much detail so let's talk about it in much detail in the lecture. So you should go to the lecture if you do not know what a non-holonomic constraint is. Okay, and then we have been given the kinematics of a single wheel. Okay, so kinematics is just how does the wheel move, right? So you can see that if you say that the velocity. Now, since velocity along E2 is zero, the velocity will always be along E1. Okay, so let us call this as V. Okay, so what are the states of the coin? Okay, what are the quantities that represent the configuration of the coin? Okay, that like fully define where is the coin and in which orientation. Okay, if you are not assuming that the coin is falling, okay, then it can be represented, the total configuration of the coin can be represented using only three states. Okay, using only three variable, the xy position of the center and the angle phi of the coin that the coin makes, that this even basis vector. Okay, so this is, I think we should write it properly. So this is your small even. Okay, so if the velocity is v, okay, then x dot is v cos phi, right? And y dot is v sin phi. Okay, and then what is phi dot? Phi dot is essentially the rate at which it is being rotated. Okay, because it has to be an external agency that you know changes this phi. Okay, because it cannot change on its own in this setting. Okay, so if you want to write this in matrix form now, okay, so this gives the form of the equation, okay, that is there in the notes here. Okay, so this is, okay, so cos phi sin phi 0 times v. Okay, so the v and omega are the input to the system. 0 0 1 omega. Okay, so this is how the single wheel kinematics has been arrived at in this particular slide. Okay, and then the lecture has progressed towards the two-wheel robot or the bicycle model. So this is a very useful model, and it has been used extensively in autonomous vehicle literature. So even the cars, right, the four-wheeled cars are approximated as by this bicycle model to keep the model simple. Okay, and again, so this front wheel is used as a steering. Okay, and this back wheel is used to generate velocity. Okay, so now in this particular case, the overall orientation can be changed through phi. Okay, but to change, like as it is reflected in the equations also, okay, that psi dot now depends on phi. Okay, but now this steering angle, okay, steering angle is provided by the user. Okay, so this is the control input to the system. Okay, now there are just progressions to all these models, and then for wheel mobile robot, one of the most accurate models is the four-wheeled model with Ackermann steering. Because what is Ackermann steering? It is a particular arrangement of the front wheels to avoid slippage. Okay, like because whenever a car turns, both of these wheels will be turning on circles of different radius. Okay, so therefore, because of the constraint that that is there for wheels, both of them should always be along the tangents of their respective circles. Okay, but if the angles are same for both the wheels, the constraint for either one of the wheel will be violated. Okay, because they're two different circles, so there has to be two different values, right? Two different tangents. So that is why, that is what the Ackermann steering does. Okay, so then there is a differential also in the backside. Okay, to avoid slippage in a similar scenario because of the thing. Okay, so and also when the robot is turning to avoid slippage, all the axes of rotation should coincide. Okay, so again, this Ackermann steering, these in the Ackermann steering, these angles are selected such that the axes always coincide with the axis passing through your rear wheels. Okay, perpendicular to the rear wheels. So basically, all your rotation axis pass through a single point. Okay, so that is the constraint that has been specified here. Okay, so yeah, and if there are multiple axes, like a truck or a trailer, like with multiple wheels, like then it becomes more difficult to analyze and model. Okay, and there is this particular term called non-minimum phase systems. So Sir has discussed what is essentially what is exactly a non-minimum phase system. So you can go to the non-linear systems theory to check what this particular concept is. Okay, and then there is a discussion about omnidirectional wheels. So omnidirectional wheels do not have this second constraint that was applied to the wheels. Okay, so the wheels are actually allowed to move in the E2 direction as well. Okay, so these omnidirectional wheels are allowed to move in the E2 direction. Okay, and then there are different models for these for the WMRs or wheel mobile robots with omnidirectional wheels as well. And this mapping is actually really important in any system that you work with. It is the mapping from the inputs that you give to the outputs that you want your system to have. Okay, you want your system to have a particular velocity, but to achieve that velocity, you need to keep, you need to give this particular rates to your wheels. Okay, so this mapping is important for like not this exact, but this type of mapping is important for every robot. Okay, so you should keep that in mind, right? So yeah, again, this is analogous to the manipulator inverse Jacobian, right? Because for manipulators also, the Jacobian related the end effector velocities to the joint velocities. Okay, and if it can be converted, if this can be inverted, it means that the WMR can be controlled using these particular variables. Okay, and then there is the discussion about modeling of slip. Okay, so now when we are talking about slip, the first constraint also that was being talked about is that there is rolling without slipping. Okay, now this is also being relaxed. Okay, and what is wheel slip? Wheel slip is basically the difference between the rotation of the wheel about its own axis and the velocity of the contact point. Okay, or you can say that the net velocity of the contact point is more than the velocity due to the rotation. Okay, so if either one of them mismatches, that will lead to wheel slip. Okay, so and again, like to generate forces, something has to deform, right? Because again, stresses are related to strains. If you do not generate, if no strain is there, there cannot be any stresses, and stresses reflect as a forces in systems, right? So either the wheel or the ground must deform to generate tractive forces. So these concepts you should just understand them really well. What do they mean to answer these assignment problems? Okay, when you're tackling those, because there are no numerical problems in these assignments, but they are more based on theory. Okay, and what are the intuition behind all these models, all these different methodologies. Okay, so like then there is further discussion of modeling of slip. Okay, with the translation and rotational dynamics of the deformable wheel. Okay, so again, Sir has discussed about this, and then there is the equation of motion from the Lagrangian formulation. Okay, so You just write the kinetic energy of motion. Okay, you just write the kinetic energy, potential energy, and use the Euler-Lagrange equations, okay, to get the final equation of motion. And this particular case does take into account slip, okay, in the form of these forces, right? Because it has been modeled here, right? The tractive force and the torque applied. So then there was a discussion about the control, right? And there was application of PID control here, and it turned out like now once you have decided to apply PID control, then you can always directly use your control partitioning and all. Yeah, so this is your control partitioning that was discussed in the previous week. And what is important is the intuition from these experiments is that performance of PID controller is actually quite poor for this particular case, right? And so you should be more vigilant, or you should pay more attention to the conclusions that you have. Okay, so the methodology is important, how you arrive at a conclusion, but it is much more important to interpret the results, to interpret the results better. Okay, like why is the performance of PID controller poor for this particular case, right? Can it be improved, or does one have to use entirely different, control techniques for wheeled robots? And also, the control, the PID control was being applied on the Cartesian path of the robot. Okay, but now one can also try to apply the PID control directly to the wheels, right? So that will involve using the transformation not from force to torque, but from Cartesian space variables to the actuator variables. Okay, I'm not talking about, like, you can also say joint space variables. Okay, then again there was this was the discussion for flat terrain. Okay, then there was discussion for uneven terrain, and for uneven terrain, okay, there was a discussion of how do you model the surface first, the uneven surface, and then how do you model slip on uneven surface. Okay, so now the main concepts about modeling of slip on uneven surface are to get the complete dynamics, including the slip for wheels on uneven surface. Like sir has discussed these in the lecture, and also there is a paper that you can refer to if you want to look into it more deeply. Okay, but what is essentially does is it, like, the lecture notes further talk about modeling of a surface, that how is a surface model. Okay, so a surface is a 2D uh, geometry, right? So that is why in parametric form it can be represented by two variables. Okay, so whenever you write, so what it means is that you only need two independent variables to fully specify the surface, right? So if you're trying to write the surface or trying to represent the surface in 3D using three variables, then there will be a constraint associated with that particular surface, right? And for a flat surface, we know that that particular constraint is that ax plus by plus cz plus d is equal to 0, right? So all these x, y, z are not, so this is a flat surface. Okay, so x, y, and z, they are not independent. Okay, once you have chosen, let's say, x and y, z is automatically defined by this equation. Okay, so that is why in parametric form you choose the independent variables. Okay, so these for a surface will belong to R2. Okay, And like more precisely, what as it has been written in the lecture, okay, if it belongs to a surface U, then this U must be a subset of R2. Okay, it can be the complete R2 as well, but in a general case, we can call it a subset of R2. Okay, and then there are like different. There is the discussion of modeling a torus-shaped wheel. So essentially, how do you model a torus? Using the parametric form, and this is the mapping from parametric form to the Cartesian or the 3D form, in Euclidean space. And then there are discussions about different quantities related to surfaces. Okay, like one is the metric of a surface, one is the curvature form, okay, that defines bending in plane, okay, and one is the torsion, okay, that defines bending like, out of the plane on a surface. Okay, so again, like these quantities have been derived for the torus because a wheel can be s- approximated as a torus. Okay, but now again, we are not talking about deformable wheels here. Okay, this discussion is for smooth and hard terrains only, right? So the terrain is also smooth and hard, and the wheels also, they are not deformable in this particular case. Okay, so now there are other ways also of representing uh, surfaces. Okay, and one is the use of cubic or B-spline functions. Okay, like it has again been discussed here. Okay, and then there is the kinematics of contact. Okay, that if you consider two-wheel robot, okay, like there is a single wheel like this, there is axle, and then there is another wheel. Okay, and this system is on uneven terrain. Okay, so the surface at both these points are modeled differently. Okay, U1 V1 and U2 V2, and then there is an overall rotation of this thing, right? Okay, if you see from above, okay, I draw the top view. Okay, it will mostly be like this. Okay, so this particular angle, right? You can call not this this particular angle from horizontal is phi. Okay, so to define the complete motion, you have to define the relationship between how does the surface change relate to the change in velocity of the rope, right? And then lecturer has given equation of motion directly for that, the kinematics. Okay, and then there is a discussion of two type of contacts. That if what if there is pure rolling, and then there is pure sliding, right? And then you can try to take combination of those as well. Okay, so after this analysis, the kinetic analysis shifted to lecture shifts to dynamic analysis, okay, of WMRs on uneven terrain. Okay, and then again you can try to go through this, and if you like you it will be all apparent once you see the lecture. Okay, then again there is a 3D of configuration, okay, for a three-wheeled mobile robot with 3 degree of freedom. Okay, and if it has more degree of freedom, okay, then you can go with more complicated models, right? But again, keep in mind that the constraints at the contact points will be non-holonomic because they will constrain velocities, and those constraints will not be integrable in the form of your position or angular position. Okay, so they will always remain in the form of velocities. Okay, So yeah, this was the case that was being uh, considered here. Okay, fixed length axle, moving on uneven terrain, and can slip. Okay, but nothing can deform in this case. Okay, and then the last lecture, it talked about kinematics and dynamics of WMR on uneven terrain. Okay, so full kinematics and dynamics, taking either the 6-DOF model. Okay, yeah, so starting with the 3-DOF model, sorry. Okay, and then so I did analysis of this. Okay, so basically getting all the equations necessary, okay, all the representations, and for writing the dynamics of the system, okay, using Lagrange's method. Okay, you can always use Lagrange's method to write the dynamics, okay, but in first, the only the kinematics was being considered, okay, that how does the quantities change with each other, okay, and that was done for the orientation and position of the wheel, okay, and once you do solve for first for direct kinematics and then solve for inverse kinematics using the direct kinematics equation, okay, then you can move on to the dynamic analysis. And to write the dynamic equation of motion, one method that has been discussed here and that is quite useful is the Lagrangian formulation. Okay, you write the kinetic energy, you write total potential energy, and then you use your Euler-Lagrange equations to write the final equation of motion. Okay, and in the Lagrangian formulation, always you can always take into account the constraints that are there for the system. Okay, so yeah, the constraints come like this, and these Lagrange multipliers that are there with the constraints, they are essentially the constraint forces, right? So like these constraint forces can be used to model slip as well. Okay, then there is just a method of solving these equations. Okay, and then yeah, the one thing is stability analysis, that if the robot is on an uneven surface, will it be stable or will it not be stable? Okay, so and what does it mean by unstability for a case of WMR is that the robot can either tip over or roll over. Okay, so on an uneven surface. Okay, so to avoid that, one stability measure has been discussed. Okay, and what does this measure mean is basically for any two wheels, okay, that are on ground. Okay, okay, so for any two wheels that are on the ground, okay, so the net force, okay, at the center of mass. I think I should make it much properly. Okay. Hmm. Okay, so now that's force, the center of mass will experience forces due to the forces on the wheel, right? Because otherwise, where will the external force come from on the robot? Okay, so the resultant force, okay, now this is the location, assumed location of the center of mass, right? This particular position, we'll call it G. Okay. So the resultant force at the center of mass, okay, if it is called FR, okay, if it makes angle theta 1 and theta 2 with the lines joining center of mass to the point of application of force or the point of contact in this case. Okay, so this stability measure has been defined as the minimum value between theta 1 and theta 1 and theta 2 multiplied by the magnitude of Fr. Okay, so essentially to have the largest possible measure of stability, the theta 1 and theta 2 must, yeah, like we should always try to keep theta 1 and theta 2. Okay, so this Fr should lie in the middle, okay, of this particular triangle, triangular cone, whatever you want to call it. Okay, so what this triangle formed by these 3 points, okay, center of mass and the two contact points, the resultant force should pass through, or you can also say that the resultant force should, yeah, it should pass through the median of the line joining the two contact points. Okay, such that both these angles are equal, theta 1 and theta 2. Okay, that is when the robot is most stable. Okay, and whenever either one of them becomes zero, okay, so whenever this zeta is positive, is greater than one, no, greater than one, it is positive, it is stable. Okay, when it goes to zero, okay, like that is the case when we call it marginally stable. Okay, that the robot is just about to tip off if not taken any action to increase zeta. Okay, and when it becomes zero, okay, that is when the robot will tip over. Okay, so this particular measure encodes these three conditions in a single variable. Okay, so you can always use this variable to keep this resultant force such that your zeta is positive. Okay, so again, this can be done for n number of wheels, like however number of wheels you have. Okay, so this Fr in this particular case, it is in the triangle. Okay, but if you do it for a three-wheel case, okay, then it should be inside the pyramid formed by all the wheels. Okay, so yeah, then there is the calculation of the resultant force. Okay, so it is not something that much worth going into in this particular session. Okay, now again see that in this case, since there were only two lines, since there were only two contact points, there were only two angles. Okay, when there are multiple wheels, so there will be multiple lines. So you take the angle between the resultant force and that particular line joining the center of mass to the contact point of the wheel. Okay, then there are numerical results for this. Then, like what you should again always keep uh, into what you should also keep in your mind is interpret the results. Okay, like just take a look. Like I'm scrolling through the results because I'm assuming that you have gone through the lectures and sir has given you enough intuition. But when you're going through it yourself, okay, you should stop and look at the results. Try to interpret them in your own way, right? Like what does the result mean? What does the result mean? Okay. And then, as always, I would highly suggest going through some of these additional reading materials if you want to get a better understanding of this particular topic. Okay, so I think I will end the session here.